Hello. Today we'll talk about a little bit a niche topic, maybe, but a very important one, namely managing beliefs of AI agents. I'll explain what I mean by beliefs, and then I'll show you some ideas about more systemic or systematized approach to managing beliefs, because most of the time in game AI we do this in a custom way, per game, and it's not very maintainable. First, a little bit about myself. Mainly, I'm an AI programmer. I started in the mobile game industry. I dealt mostly with traffic simulation in simulation games. And then I got more interested in strategic games or tactical games and joined QED Software, where I'm a co-creator of a great AI framework that has been used in our games and in third-party games like Ancestor's Legacy and now in Hard West 2. Okay, so first I'll talk to you a little bit about the problem. What is the problem that we are trying to solve with our techniques? Then I'll highlight some challenges, and then we'll pass to the main part of the presentation, where I'll explain a little bit about the algorithmic side of storing observations, querying observations, and symbolic logic, and reasoning about beliefs. Okay, so I'll show you two main classes of problems that we want to deal with using these techniques. First one is a complete lack of situational awareness of AI agents, meaning that, for example, in stealth games, you can wander around the level, opening all the doors and messing with all the crates and all the movable environment elements, and the AI agents don't even notice because they don't have the memory of the previous game states, of the previous world states, so they don't even notice any important changes. They don't notice missing allies. For example, if there's a patrol route and for example, there are two guards, and one is gone for like 10 seconds or 20 seconds, it hasn't been seen, other agents don't even respond to this like they should. And the most recognizable one is the famous quote from Skyrim: "It must have been wind." Like, you shoot the agent for the third time in the knee, and still the agent doesn't have any memory of previous events, so behaves in a very predictable way, which can be a good thing. But when it's predictable and just when it's predictable all over again, when you do the same things all over again and the same behavior repeats, it starts getting very tiresome. And the other one, mostly exhibited in RTS games or all sorts of strategic games, is cheating AI, because dealing with hidden information and managing information is such an underexplored topic in games. Many developers resort to ugly tricks, like boosting health or giving more resources to AI agents, or even giving access to restricted information that the agents shouldn't have, like seeing under fog of war and these sorts of stuff. All right, so this is like as high level as can be displayed a standard AI agent loop. First, we start with perception. These are all your raycasts, your cone of vision checks, all these sorts of stuff. Then we proceed to decision making. Mostly in game dev, people use like those glorified. I call them glorified scripts, like for example behavior trees. But it can be basically any decision making technique that generates behaviors and selects the best one in a given situation. And then we proceed to performing an action. And in my opinion, what's missing here is this little block between perception and decision making, and that is belief building. And what do I mean by belief building? First is a structured storage of all sorts of observations, like enemy positions, like health states, anything that you can imagine. And then reasoning about hidden information based on the information that was observed in the past. Okay. So what are the challenges? Because, as I said, this is an important topic, so we have to somehow explain why don't people do this in a systematic fashion. First one is that the data, the perception data or belief data that we have to store is very heterogeneous. We have to store also all sorts of data like positions, Boolean states of doors or crates or anything, numeric parameters of agents, events, for example, explosions on the map. You just see, for example, an explosion that's not tightly bound to a given object. It's just an event in the world. And basically, you can envision any kind of custom data, custom perception data. And what's more, those values have to be structured in a way that, that captures the passage of time. That, for example, a given health value was held between the 0th and 10th second of the game. So we have to operate on time intervals. And the other problem, I think that more important one is that we want our agents to exhibit a kind of common sense reasoning. And most of common sense reasoning that is performed by humans is largely symbolic. For example, we can operate in such heuristic rules like, if my companion disappeared not too long ago, the enemy has to be relatively close. And as you can see, I used those vague terms like not long ago or relatively close. And we need to somehow bridge those worlds, the world of the symbolic high-level description and its meaning in the numeric data. Okay, so we'll now proceed to the part when I'll explain how we approach storing observation, meaning the perception data in a systematized fashion. So why do we? I think that this slide may be a little bit spurious because I already explained why we need a memory system. We need to provide the information about the current state, the past state. We need to reason about hidden states, about hidden information based on historical observations. And we want to also monitor results of the agent's own behavior. For example, we want the agent to remember that a given behavior was, for example, failed 3 times before, so that the agent doesn't try to do the behavior again. And these are some, I would say, the most obvious use cases of such a memory system. For example, we can query for last observed values of various properties, about past values, check variability. For example, if we want to detect medic units, we can look for sections where there are sudden changes in other agents' health. And all sorts of queries by predicates. For example, we want to find all the characters that were spotted visiting a given room in a given time. And let's proceed to the data structures. Our approach assumes, I'll start from the end, assumes that the world is structured by dividing it into so-called world objects or entities. I'll use world objects and entities interchangeably. And a world object is simply an unique entity identified by an ID with associated observation streams. And those observation streams are pairs of values and time intervals. For example, as you can see on this image, we have an enemy and a health and ammo stream. And for example, we know that from the 30 seconds to the first minute of the game, the enemy had 100 HP, and so on and so forth. And the basic loop of such a system starts with a game state change, for example, a triggered event or anything like that, or maybe a periodic update just with some fixed timestamp. Then game data is processed into a simplified or just extracted data that we care about, and is registered in the system with a given timestamp. And then all those observations are sorted. Those neighboring entries are merged if they overlap or are close enough to each other. I'll explain that later. And then we can, but we don't have to remove old data, for example, to save memory. Okay, sorry for the resolution. So this is how we'd like to interface with the game world to make the system game agnostic. Here we have the game world. which is totally specific to the given game. Then we have a perception system that serves as a bridge between the game world and our memory system. And here in those observers, like position observer, health observer, this is all the custom engine-specific perception code that you would have normally, like raycasts, triggers, cone of vision, this kinds of stuff. And then we have an entity registry, and this is a system that lets you map from the real-world objects, like game objects in a Unity engine and actors in Unreal, to unique IDs. And then the memory system only deals with those IDs and perception data. So we can reuse the memory system from game to game without making any assumptions that we have to, for example, work in Unity engine because we somehow have embedded assumptions about, for example, game objects being present or components or actors in Unreal Engine. Okay, so here's a basic flow of adding new information to the agent's memory. First, we start with an empty. This is an observation history of a single soldier that our agent observes on the map. So first, it starts with an empty entry because we didn't have any opportunity to observe anything, and then new observations appear. And they are just simply stored in those streams. And then, this is, I believe, the most important part. The most important part. Those two observations get merged because they are very, very close to each other. As you can see here, the x-coordinate is 0, here is 0.03. So they are close enough that their timestamps can be merged into a larger interval. So, and what it means to be close enough is defined by the developer. So we don't want to like spawn we don't want to spawn a new observation every frame because the agents like moved a little bit to the left or a little bit to the right. So we can specify a radius in which the agent can wiggle around, and still it's interpreted as a single observation of a single position during a larger time interval. And here, after adding another health observation, you can see that not only value closeness is important, but also closeness in time. For example, in a specific game, we may assume that health doesn't change so rapidly that, for example, 2 seconds is a long time. So if you observed two similar values of health, even separated by 2 seconds, we can still merge them in a single interval. So it just helps us store the same amount of information in a very small patch of memory. So it saves a lot of RAM. And here is some code. I'll avoid showing you code in this presentation, but in this slide it turned out to be necessary. This is C#, so if you work in C++, you'd have to implement something like those filtering operations that you have in C# Sling, for example. So here we have an example of getting the latest observation of an agent. So we pass the enemy that we care about and the name of the location stream. So in our example, it would be position. And those streams are identified by string identifiers. And then we get the latest observation and get its value. For example, here we can get all property entries of a given agent, all locations, from the two last turns. So here we have a game that has a game time. Here we specify that the threshold is 2 turns, and we get all locations, like location history during the last turns of a given enemy. And we can also perform more complex queries, like getting all enemies that visited a given room in a given time. Okay, so now that we have our raw data, raw perception data stored, we have to proceed to reasoning about it. And the thing that's most difficult is just symbolic reasoning. We have to somehow transition from these raw data types to some kind of logic, basically. And most of this of the work that I'll present in the following slides is based on work of Barbara Dunin-Kemplicz and Andrzej Szałas. They're scientists from University of Warsaw. And if you're interested in the topic of managing beliefs and symbolic reasoning, you can look up those topics that I've listed here. Epistemic profiles, rule-based reasoning. There's a specific language called 4QL that deals with this, but it's not very usable in game dev, so we just took some inspiration from it. And group beliefs. It's a big topic that I won't discuss here, but forming group beliefs and group commitments, collective planning, all these kinds of stuff is very important and is very close to the topics that I'll cover today. Okay, so what do I mean by common sense reasoning? Basically, very simple if-then rules that can be specified by a non-technical user, like an AI, maybe AI designer is a technical user, but a non-programmer. Let's say it like this. So, and those rules basically are very heuristic in their nature. For example, we may, people often exhibit such kinds of reasoning. For example, if I see a suspicious-looking guy entering the room, I'll assume that he's a thief. It doesn't have to be true, but it represents as some sort of a cognitive style of an agent. So, and the agents may vary with their styles and the rules, the heuristics that they use to reason about data. And what's important, we have to be able to represent lack of knowledge, because lack of evidence is not the evidence of absence. So we have to, in our logic, in the logic that we use to reason about beliefs, we have to distinguish between lack of data and something being false. And we have to remember that because those rules and methods that we use are very heuristic, they are non-strict, they may clash. For example, one heuristic may produce a true value for some fact, and another may produce a false value. So we have to deal with this also. Okay, so for this purpose, for managing such reasoning, we use a four-valued logic, and the values that are present in this logic are true, false, unknown, and inconsistent. Basically, true and false are what you would expect normally. Unknown is a value that is returned where there is absolutely no observation about a given fact in the system. And inconsistent is the value that we see when various modules of the system return conflicting information. Basic logical operators, like conjunction and alternative, are defined as follows. First, we introduce a truth ordering, where false is the least true and true is the most true. This is somewhat arbitrary, but it just has the properties that we want from this logic. And if you're very, very interested, you can look up the scientific papers by Andrzej Szałas, and he explains why such ordering is introduced. And then conjunction is a simple minimum operation, and alternative is a max operation. So for example, if we take false or true, it will be true. And if we take false and true, it will be naturally false. So most of our intuitions about two-valued logic are preserved in this logic. And the funny quirk about this logic is that negation does not transform unknown and inconsistent. Because if we have no information about something, if we negate all entries about it, it's still unknown. And the same is true for inconsistent. If we have conflicting information and we negate the information, it's still conflicting. So negation is neutral with respect to unknown and inconsistent. Okay, so how do we represent facts in this logic, using this logic? First, we define relations. And relations are basically in their, I would say, how to phrase this? In their nature, there are basically labels, like names, that connected with types. For example, we can specify a relation attacked, and this relation has three arguments. And the character that performed the attack, the character that was attacked, and the weapon that was used to do this. For example, it's just a simple example. And then to this relation and the argument list, we attach the logical value. Here in this example, it's false, but it may be true or not anything else. It can be false or true. We'll deal with unknown and inconsistent in the larger system. And here's another example when you can see that also numeric values can be attached. It can be arguments of those relations. For example, we have a relation have met, and we have a Jack and Ellie, and this representation means that Jack has met Ellie 5 times in the past, and it's true. And what's important, we can represent also negated facts. For example, we could have said that Jack has not met Ellie 5 times in the past, and we would just attach a false value to this statement. Okay, so we want to, sorry. After we represent the word state with those literals, we want to somehow process them to infer hidden information or mostly hidden information, but sometimes we want just to give some flavor to the agent, for example, to make some far-reaching assumptions that are not guaranteed, but we want the agent to exhibit them. So we start with defining rules. Rules consist of so-called preconditions or constituents that are basically any clause or sentence in the for-valued logic, and a consequence that are a conjunction of facts. And they are strictly a conjunction because using alternatives in the consequence introduces a lot of complexity, computational complexity, that can be dealt with in separate modules. So in our rule-based system, we don't use alternatives in consequence. So here are some example rules. For example, if the player stole the treasure and they're not currently seen, they are headed for the exit. This doesn't have to be true, but it describes a cognitive style of a given agent. For example, we can have a guard in a stealth game that reasons in such a way. This assumption can be completely false, but it doesn't matter to us. We don't want our agent to be omniscient. We want them to behave in a realistic fashion. And the rest of the rules have similar structures, so I won't to talk about them too much. And when we have our storage of facts, our relations coupled with arguments and logical values, we can apply rules to such worlds. For example, here we have 2 assumptions or observations that John attacked Henry with a club and Henry is dead. And from this we can infer, if we wish to, that Henry has been murdered by John with a club. And this doesn't have to be true because you could have seen the attack and didn't see, and you could have not seen, whoa, a difficult language. You could have not seen the murder, but you can still infer such information because the designer specified it to be so. Okay, so if we would rely on only applying those rules to store data, we would, in larger systems, we could just run out of memory because we would have to produce any consequent for any input data for any rule that we have defined in the past. So we would have to store all possible facts that can result from applying those rules. So it's simply not manageable. So to reduce the need for storing all possible consequence, we use something called backward chaining. It's a similar or even identical technique that we use in planning, in action planning. And here's a little example. Let's say that we have 4 rules, that if X croaks and it flies, then it's a frog. If chirps and sings, then it's a canary, etc., etc. And then we get a query. Is George green? So we don't want, and we want the system. We don't want the system to store the information about George's greenness up front. We want it to simply respond to the query when it's asked, and we want to do this in a fashion that's performant. So what we can do, we can take the descriptor, let's call it, of the query, like green, and find all rules where green is in consequence. For example, this rule has green in its consequence, and then we locate its constituents. That it should be bold. Is a frog should be in bold, not only a frog. So first we have our query. We take green. We find a rule that contains green in consequence. Then we scour through the constituents and find other descriptors, like is a frog, then find a rule that contains is a frog in its consequence, and so on and so forth. And we do this until we stumble upon descriptors that are not used in any other rules in their consequence. And in such a way, we can reduce this chain of rules to a simple rule. If George croaks and eats flies, then George is green. And this doesn't have to be performed in runtime online. After we specify those rules, we know their consequence, we know their preconditions, so we can basically pre-compute all paths from facts to consequence through all those rule chains, and then just simply use those simplified rules when querying the system during gameplay. We can just, so I've written here that such backward paths from conclusions to assumptions can be pre-computed. So we don't have to compute them on the fly. And we don't have to store everything in memory. Okay, so now that I've described storing in numerical data and symbolic reasoning, now I explain how we try to merge those two worlds. First, we have to define we have to define a module. And a module is simply a piece of code that speaks in for-v logic. Basically, you can ask a module about a fact and be given a response. For example, you can ask, if John attacked Ellie? And then you get a simple response: true, false, unknown, inconsistent. Basically, we don't want to get inconsistent values on the output, and I'll explain how we deal with it later. And modules can reference other modules, meaning that, for example, some game-specific module can store some kinds of relations and facts, another one can store another facts, and above them we can have a high-level, for example, some heuristic module or rule-based module, and they can reference each other and ask about facts. But the thing that's strictly forbidden is cycles, because we don't want the system to just run in circles. So it's basically an acyclic graph of references between those modules. And here are some example queries about beliefs. Give me all the rooms that the player can be located in. And what can be located in means is specified by the developer. And all characters that are located near, where near also is a vague term that can be inferred from the numerical data, but for the purposes of the belief system, it's just a simple label. All allies that are missing, or units that have lately attacked a given target. So the first module that we introduced is simply the rule-based module that I described before. When we have some assumptions and some rules defined, we can ask the system about the facts that flow from the rules applied to the assumptions. The most basic modules that we have is just a simple bag of facts. We call it a belief set. For example, a developer may just want to assume some facts like this unit is an enemy, or this unit is suspicious, and can directly enter those facts into the system without resorting to any algorithmic shenanigans. You can also have lots of game-specific modules. For example, a special reasoning module where all those cryptic terms like near, or close enough, or close to a patrol path, they can be interpreted in a game-specific fashion, but still those game-specific modules can communicate with the larger system using the for-value logic. So for example, when we can have some navigation graphs, visibility graphs, and if we ask the system, is the unit A visible from region, for example, 2, from the point of view of the rule-based system, we don't care about what near means, what visible means, what region means. It all can be placed in the custom module that's specific for the game, assuming that it has the interface that we require, to the for-value logic interface. And there's another one, a very important module, is a belief base. Belief base is simply an aggregator of other modules. For example, it can be a simple OR operation. We can have like a few modules that answer questions about the same relation and want to perform an OR operation. Or maybe when we have conflicting values, like for example, in this heuristic module, heuristic module would tell us that Jack attacked Ellie, and this rule-based module would tell us that he didn't. So we have to somehow specify a fusion operation that would take those conflicting information and just return some value that's consistent. And for example, we can specify any kind of fusion function. For example, we can perform voting. If there are many such child modules, we can simply count true values, we can count false values and apply simple majority voting. Or we can resort to authority. If there is a conflicting information, just ask the specified system, because we want all those values to be overridden in case of inconsistency. Okay, so let's now proceed to the construction of the full belief system, like merging those two concepts. So it's a pretty busy slide. I'll try to explain what's happening here. So in the middle, we have the symbolic world, the belief structure, meaning those modules that I've talked about a little bit before. Here we have our memory module, where raw data is stored. Here we have the entity registry. Remember, entities are those abstract, identifiable groups of observations. Like, for example, a soldier would be an entity, or a door would be an entity. And here we have some game-specific code. Here we have some level data, for example, navigation system, line of sight data, all those sorts of stuff. And above this all, we have our decision-making algorithm, like a behavior tree or maybe utility, anything like this. And our decision-making algorithm asks the belief system about the game world and generates behaviors based on those queries. And here you can see that we have a custom module, like spatial reasoning module, that can reference game-specific modules and our observation data. Here we have just simple facts, like is safe, is complete, is alarmed, where we interpret the numeric data to produce such symbolic labels. And here we have those generic rule-based modules and generic fusion operators that just perform actions strictly on those logical values, and they don't deal with numeric data that's underneath. And as you can see here, we have the memory module that deals with time, and here we have a strictly logical module, and we can use this combination to introduce time into symbolic or logical reasoning. For example, if we want to query about a fact in the past, we can simply specify that based on the data from second 1 to second 4, it was something true. And the system would just simply ignore the data from the most recent past and interpret the data from the specified range. And also, thanks to the fact that we have the memory system and we have these special temporal data stored, we can express complex dynamic concepps like is flanking. Is one agent flanking another, or is one agent moving away from someone? Because we may want to generate some behaviors. If the agent is running away, then we want, for example, to bar his path, or we want to pursue him, or all sorts of stuff. So thanks to the temporality of the memory system, we can express such concepts. And for example, if a character's health increased rapidly, there's a medic nearby. So increased rapidly would be simply implemented by the developer as they wish, but the rule is still reusable even between games. And this is important, that if you make another game that's quite similar to the previous one, you can simply decouple the game-specific logic of the first one and transfer all those rules and the symbolic system to another one. It will work, and it will just expect you to provide it with definitions of such terms like increased rapidly. So let's walk through a very simple example of a game where you use the systems to reason about the world. First, here. we have a simple AI-controlled guard character, and the aim of the character is to find and destroy the player characters. Everyone knows this from any stealth game that you've played. And the level consists of many connected rooms. So in our belief system, we simply define two basic entity types. First is the character, the player character, and then a room. A room. And then we define relations. Is the agent currently observed? Last seen inside is a relation telling us that a given character was seen in a given time, in a given room. We can have some facts about rooms. Is room 1 reachable from room 2 since a given time by a given character? And then a simple relation is a character inside a room. And here is our one single rule that we'll use. If the character is not observed currently and was last seen inside a room, a given room, and another room is not reachable from this first room since it was observed, then the character surely is not inside another room. And in this way, we can just filter out all sorts of locations that are not even suspicious. And we can, for example, generate exploratory behaviors in this way. Then we construct the whole belief structure, where here we have, as usual, game-specific perception code, the memory system. Here is our, for example, we can call it a location checker modules that answers the questions about the relation is last seen inside or reachable since, those two relations. Here we have a sense module that can answer the questions about is a given character currently observed and is the character seen inside some room. And then we fuse those two. Those two modules so that our rule-based system can ask them both at the same time. For example, we can just apply a simple OR operation to these two worlds. And as you can see, those two modules can reference level data in an independent fashion. So those vague terms like is inside can be checked in game numerical data, for example, by checking room bounds or some colliders or anything like this. And here's an example behavior generation that we can perform after reasoning about hidden information. The most simple situation is that the player character is observed, so we just attack the character. If it's observed and it's inside another room that our agent is, we can go to the room to pursue the character. But if we have no information about the is inside label of menus, we can only generate exploratory behaviors for these rooms. So if we filtered out all rooms that are unoccupied for sure, and for sure meaning that this simple rule. So if we deduced that the agent cannot be inside a given room, we simply ignore the room and generate exploratory behaviors only for rooms that are unknown, whose state is simply unknown. And yeah, this is the whole description of our belief building system. And in the future work, we'll deal with forming group beliefs, meaning that when you have groups of agents that possess such systems, we can try to construct some kind of temporary group belief. For example, for a given goal, if we have an agent that has seen an enemy, for example, to the east, and another agent that has seen the same enemy to the west, we have to somehow make their individual beliefs consistent so that they can act together and plan together. So this is a next big step for our system. Next, this is still very uncharted waters. We want to deal with negotiation and argumentation. For example, in games with companions, where you can, for example, you see some part of the game, the companion sees another part of the game, and we want to communicate to the companion that, could you please attack this enemy? And the companion should have the ability to respond in an intelligent fashion, based on their own information. For example, that this action is not possible, or maybe we should do something better because I have some more information about another part of the game. So this is very difficult. We're currently prototyping a game that uses such a system, but still I don't have anything very systematic to show you. And then, of course, collective planning and commitments that stems from such mechanics. Here's some literature. If you would like to read more about belief structure and reasoning, you can check out those too. And there are basically the founding papers that we were inspired by. And here's the project that we are part of. It's called Fogs of War. And this is the conclusion of my talk. Thank you so much. And if you have any questions, please ask away.
Thank you, Rafał. Thanks a lot. And now, as Rafał said, it's time for questions. So if you have any, here's a microphone. You have to stand and go to it, and feel free to ask. Yeah, we have one.
Okay, so thanks for a very nice talk. And I have two questions about those memory arrays. So you mentioned that some of the values can be merged, but how do you limit how many items can be on that array? So what the AI remembers?
So the developer just defines three basic values. First one is like the closeness checker. For example, if those two values are close, a temporal closeness checker, if they are close enough in time, and a threshold, for example, we call it a forgetting threshold. So you just specify a timestamp after which the old information can be simply discarded.
Okay.
So for now we have this, but maybe we should consider also specifying some more complex, like forgetting strategies, because we may have to store some old information and discard some newer information that's simply irrelevant. But for now we just use a simple temporal threshold.
Okay, so so now my question is about the initialization. Sorry. How do you start the AI? So when, for example, an AI enters a dynamic place and like what he remembers or what he starts with, how do you initialize it?
So first you have to specify, maybe I have a slide here. This one. So first, before even starting the game, you simply specified what kinds of objects can be seen on the level, and what kinds of information streams or observation streams are bound to those entities. And then when I'll show you another slide. I can't find this. Oh, here. So then here you have your game-specific perception code. For example, a game object stumbled into your trigger, like your vision trigger, and it has a certain component that you care about. So you extract the observation value, and then you perform some kind of mapping between a unique ID and this component. And then it just gets stored in memory. So the basic initialization is just defining the entity types, defining the conversion between your game-specific types and those unique IDs, and then just you specify the observed data, those observation streams, and that's all.
Okay, thanks.
I want to ask about this true, false, and unknown states. Why don't you use float to describe probability?
You can...
Because it seems natural, and if you have 3 rooms and enemy was seen in one of them, maybe it is more probably he is still in this room. Are you missing some information?
Yeah, I think that introducing fuzzy logic, like float values for truth, it introduces some computational difficulties, because when you have the third value unknown and you have to somehow define what does it mean to, for example, an OR operation or an AND operation, they are well defined in a standard fuzzy logic when you have just a single float value. But when you add unknown to the system, it simply gets really. We have no well-defined fuzzy logic that contains the unknown value. and we cannot properly, we don't know of such a logic that properly defines the unknown property. For example, if you have unknown or something, then how do we merge the unknown label with a float value? It's very, it's tricky.
You incorporate such rules for unknown and I don't know how it was called, the fourth state.
Inconsistent.
Yeah. So maybe in
but for example, in fuzzy logic, it's very difficult to define inconsistency, because for example, one system may return a value of, for example, 0.49 and another one of 0.50, and maybe you could try to define inconsistency by a too large discrepancy, but we stumbled upon many problems when trying to reason about 4 logical values in fuzzy logic. It's simply it's just simpler to deal with discrete values, and if you want to perform such fuzzy operations, for example, like deal with probabilities, you can simply move them to a module that deals strictly in fuzzy logic, but then when it's asked by the reasoning system, it just simply performs some kind of discretization. For example, you can have a threshold probability after which you assume that something is true. So you can
one module can use fuzzy logic inside, but
there's the assumption about the fourth value logic is only inside those belief structures, but individual modules can use any logic that they want.
Okay, I see. Okay, thank you.
Hi. Hi. I've got a question about you said that when for the frog example, if green, then it means it croaks and it flies. So you can pre-compute that, which means that if green, that you don't have to reason about all the middle steps, you just know which data to access. Yes. So my question was, do you do any pre-optimizations about how you store those data? For example, if let's say if the green query is something that happens often in your game, do you store the croak and eat flies data together in your memory, or do you do anything like that?
No, we don't, but it's a good idea. Yeah, because memory access is our the main consideration, performance consideration. But no, for now it just stored in a unified fashion. So.
Right. Yeah, because I was wondering, because of those data streams can get. I would presume that even with merging, they can get quite large, and
yeah, they can.
And
yeah.
You probably have hard time meshing those data together from the different streams.
Because the memory can end up very fragmented when you have many agents with many disparate observation streams with different kinds of data. Yeah, it can get a little bit fragmented. So maybe we should consider custom allocators that would just squash it all together. Yeah.
Okay. Thanks.
Thank you. Oh, one important thing. We have a booth on the first floor, so if you want to visit us and talk about technicalities and code and see our tools, you can just go there and ask us.